Okay, everybody. So today we're going to be talking about estimations. That'll be today's topic, and then we'll do part two. I'll upload a video on Tuesday and give you an assignment based on this. Again, the assignments are going to be as straightforward as possible. I'm really going to try and, I'm not going to throw any tricks at you, obviously. I mean, not that I ever do, but given the fact that I can only give you a couple examples here and work one out for you, I'm just not going to stray too far outside the box. So the assignment should be, pretty straightforward and nothing really, nothing surprising. So let's go ahead and get started. I think estimations, the logic behind it, I think is going to be pretty clear. It's definitely less theoretical than like the central limit theorem, the stuff we did on Tuesday. I will say though that of all the things we do in class, this may be the most applicable or the, has the most real world relevance, just because you've seen this stuff before. Whether you know it or not, you've seen confidence intervals, and you've seen how they're reported. And, part of the goal, I think, is to help you guys become more literate statistics consumers. So, basically when you see garbage, you'll be able to recognize it, kind of the point. But yeah, today the estimation stuff I think is going to be super applicable to your lives. You've seen it before, and I think it's going to be straightforward. A couple equations, but nothing super complicated. So let's go ahead and get started. All right. So think back to last chapter, the central limit theorem stuff and the sampling distribution. The question is, how do you estimate population means and proportions based on the principle? Let me correct that real quick. The principle of sampling distributions, okay? So it's kind of like, think about it. We take a sample from a population. How do we know that that sample has anything to do with what the population mean or proportion is? How can we be sure that the sample represents the population itself? Obviously we do the random sampling, but you might be thinking, like, how can we be so sure? Hopefully. It's kind of a skeptical way to think, but I think the right way to think. Okay, so what estimation is this process where we select a random sample from a population and use a sample statistic to estimate the population parameter. Really simple. It's how we take a sample, get the statistics, and how do we know and how do we tie those to the population parameters. Right, so something like we take a sample of 50 people from VSU and we get their average age. How do we know that that average age of that group represents the population, and how accurate are we? That's kind of what the estimation stuff gets into. Is it tells us how precise and within what kind of range of error that we have. Okay. All right. So two kind of key definitions. Point estimates. So this is kind of what we've done up to this day, up to today has been getting point estimates. The mean number of children that people have in this sample, the mean number of email hours, the mean number of poor mental health days. Think back to all the examples I've given you. Pretty much everything I've shown you, we've gotten sample statistics that are point estimates. Okay, so sample statistics used to estimate the value of a population parameter, we call those point estimates. But the problem is we don't know how accurate they are. We don't know with any degree of certainty how close if we get a sample. Let's go back to the VSU example. Let's say we take a sample of 50 people at VSU. We find the average age is 20. Well, how do we know how closely that estimates the true population number? We got that point estimate, which is great. But what we really want to do is focus on confidence intervals. So confidence intervals are the range of values defined by the confidence level which the population parameter is estimated to fall. You can think of this as margin of error. So think of all the things you see that have margins of error. I've been thinking a lot about, well, obviously the viral outbreak is kind of first on my mind, but before that I was thinking a lot about politics and political polling, and you've seen this stuff where, a candidate's polling at, say, 40% plus or minus 5, the margin of error in this search. So you've heard all those words before. All that's referring to is a confidence interval, because at the end of the day, what we're actually estimating is not a point estimate. So we could say that the point estimate we get of, mean age being 20. But what we really want to know is what's that confidence interval around it where we can be a degree of certainty that it's between these numbers. So if you're thinking, big picture, think about the confidence interval as sort of a range of values, and it increases our accuracy. So really what statisticians do, we have to get a point estimate, but then we draw a little confidence interval around it based on the margin of error. And that's what we're going to look at today, is how to calculate that kind of stuff. Okay? Confidence level is the likelihood expressed as a probability or percentage that the specified interval will contain the population parameter. So we could say we generate a point estimate, right? You get a mean value. You draw, you get a confidence interval around that based on how much error. And then we can say to what degree of confidence that we have that the true value falls within that range. Because ultimately what we're trying to do is gather sample statistics to estimate population parameters. We take a sample, we get a statistic like a mean or a proportion, and we want that to represent the population number. How sure are we? Well, we use, and hint, we use the standard deviation to draw these confidence intervals. And, based on what our confidence level is, we can say with a degree of certainty, like we're 95% confident, 90, 99, 90. There's nothing magical about these numbers. It's just sort of, what's the word for it? It's just kind of common practices. Scientists, for whatever reason, like that 95% confidence level or 99. Now, certainly the idea is that if we're 90% confident, that means we're less confident than 95, which means, which is also less confident than 99. The flip side of it is if we're 95% confident in our result, that means we're 5% not confident. So keep that in mind too. We can never be 100% certain of anything, such as life. Anyway, so margins of error are basically the radium of a confidence interval. So the margin of error tells us how much width is in our confidence interval. Okay, so let's do a little example. This is, the best way to do this stuff, obviously, is examples. I'm going to do one on the screen and kind of work one out for you. Obviously, please make sure you're reading the book. This example is straight from the book, but then there's one that's not. So anyway, okay, so imagine that we took a survey of 500 students on our campus, okay? I said 15,000, that's probably a little high, but I kind of wanted it to be even numbers. And this example is in the book, not the, well, I'm not sure if the number of students is. Regardless, this commuting example is in the book. So basically, they took this sample of 500 people, and they asked the 500 people, how many hours a week do you spend commuting to campus? And they found that within a sample, so here's your X bar, sample mean, 7.5 hours a week. Okay, so you think about if you go to campus 5 days a week, that's about an hour and a half commute time. For both ways each day. 7.5 hours a week for commuting. Obviously, this campus must be a more commuter-based campus. Anyway, so we have the sample mean. Obviously, we have sample error. So, maybe I shouldn't say obviously, but think about this. How could error be introduced to this sample? Well, people don't know exactly how much time they spend traveling, so they kind of estimate it. Maybe this sample of 500 people, so obviously the key is that they have to be randomly sampled, but we don't know. Maybe the 500 that were randomly sampled tended to be people who were at a distance. So the 500 people we picked, maybe, we got a lot of people in there who are traveling from far distances and less that are really close, or vice versa. The point is that when you take a sample, there's always error. Period. When you have a population and you take a sample from it, you're always going to have a little bit of error, whether it's response bias or recall bias or just randomly getting individuals who are really high on the distribution or low. There's always going to be a little error. And in knowing that, when we get the point estimate, that's when we draw the confidence the confidence interval around the point estimate to give us an indication, well, here's the point, but we're confident that it falls somewhere within this range. Again, statisticians are less concerned about, we really don't estimate exact points. We're always looking at estimating an interval, a range of values. Okay? So based on the central limit theorem, though, we know that with a large enough sample size, remember there's no general rule, but about 50, and obviously we have that here, most sample means tend to be close to the population mean. So we know that we're probably close, but we don't know exactly how close, and we don't have any way to tell other people how close we are. So that's what we're doing today with the confidence intervals. So sampling distribution of the mean is approximately normal. So think back to the lesson that we did on Tuesday, the central limit theorem stuff. If you need a refresher on that, go back in the book. But because we know that, we can make this assumption. Because we know how theoretically on a sampling distribution, how those means are going to line up, we can say something about the general precision of our estimates. Without the central limit theorem, we couldn't do any of this. Without random sampling, we couldn't do any of this. So, what underlies all of this is the assumption that we're randomly sampling. Okay? Okay. So knowing this and using the central limit theorem, we can use the normal distribution to determine the probability that the sample mean will fall within a certain distance measured in standard error units, z-scores, which we've done before. Think back to the z-score stuff. Of the mean or the mean of means, right? The sampling distribution mean. So the assumptions that you can make are that 68% of all the samples will fall between +1 and -1 standard error units of the population mean. 95% are between about 2 and 99% between about, well, I shouldn't say about, it's just 2.58 standard errors of the population mean. So, think back, think back to the normal distribution, right? We know within the standard deviation units, what percent of the distribution falls within that. So what this is saying is that knowing the central limit theorem and knowing how if we took an infinite number of random samples and created that sampling distribution, let me pull it up here real quick just so I can remind you of what I'm talking about. It's this. So we know that if we take an infinite number of samples, that eventually, as we continue to take samples, you're going to find that the distribution of the sample means, here's one sample and it's mean, another sample and it's mean. If we continue to gather those, we know that they would line up approximately normal around the true population mean. Let's go back here. So if we know that, that hypothetical sampling distribution, then we know that regardless of what the mean we get from our sample is, we know that 68% of the time it's going to fall between +1 and -1 standard errors from the true population mean. So let's go back to it. That's here. Here's the +1 and -1. See how 68% of the cases fall there. And you kind of have to take my word for it. I think it's pretty obvious that the majority fall within that. And then if you go down to plus or minus 2 standard error units, then you're talking about 95% of the samples. So if we know that, then we can determine how accurate our estimate is given a certain range of values. So I think it's time to work out the problems. Okay, so based on these assumptions and the value of the standard error, we can establish the range of values. This is exactly what I've been saying. So here's the formula for the confidence interval. It's really it's not super complicated. It's pretty straightforward. So a confidence interval, to calculate it, you first have to calculate the point estimate. So the first thing you do when you're calculating these confidence intervals, and statisticians, this is what we do. When we get a sample, we always get a point estimate. We get the sample mean. That's your X bar. But to create the confidence interval, we take our mean and then we add z times the standard error and we subtract z times the standard error, such that your point estimate is always going to be in the middle of your confidence interval, right? In this case, 99% confident, well, we multiply by, it's between negative 2.58 standard error units and positive 2.58 standard error units. That's our confidence interval for, a 99% confidence interval. So think about it. I mean, obviously, if you're 99% confident, your confidence interval is going to be a lot wider. I mean, if you step back and think, I could say that I'm 100% confident that the mean age in the United States is between 1 and 100. Well, that doesn't really tell us much. The range is so big. So as we increase our confidence, our interval gets larger. As we decrease our confidence, our interval gets smaller. And the examples I'm gonna show you here, I think that'll become more clear. So here's the basic steps. Calculate the standard error of the mean, number 1. Decide the level of confidence and find the corresponding z-value. So typically I'll ask for so I'll say, calculate a confidence interval at the 95% confidence level. But if you were doing this on your own, this is your decision. But like I said, typically I'll give it to you. You find the corresponding z-value. You can, you'll have to look that up in the z-table. Then you calculate the confidence interval and interpret the results. Don't sleep on number 4. The interpretation is the most important part. But we got to do all the stats business to get to, here's the sociology. Okay. So let's use the example from the book. I'm going back to that commuter's example, okay? So in the book, the example is this sample of 500 students at this campus, and they find that the mean number of hours they spend commuting a week is 7.5 hours. So see how I have my units here too. That's kind of important. I guess if I was doing a better job, I would have the units here. So the standard deviation for the number of hours per week that the commuters travel is 1.5 hours, okay? So this information will always be given to you. You'll always get these, because this is derived from the sample, okay? Okay, so let's go back. So the first thing you gotta do is calculate the standard error of the mean. So in this case, here's our equation for the standard error of the mean. I think I'm going to post for you guys just a little, what do you call it? A formula, like, I don't want to say cheat sheet, but like just a formula sheet that has all these formulas written out for you. I'm going to post it on BlazeView just so you're not having to dig around for the formulas. But this, we've seen this before. This was back when we talked about the last time when we talked about the sampling distribution stuff. So this is the standard error of the mean is equal to the standard deviation divided by the square root of n, and n is just the sample size. So this equation is really there's nothing really complicated here. To calculate the standard error, which is your first task to calculate a confidence interval, you divide the standard deviation by the square root of the sample size. So the standard deviation, 1.5 hours. The sample size was 500, so square root the 500, and then 1.5 divided by that number, and you get 0.07, okay? So that is your standard error of the mean. And if you look back to the confidence interval equation, that's kind of a key part, okay? Step number 2, decide the level of confidence and find the corresponding z-value. I decided, well, I don't think I didn't decide. The book's example, they use a 95% confidence interval. Again, I'm gonna always specify this for you. In doing your own research, you'll be able to have flexibility in this, but as far as like the assignments, I'm gonna say, here's the mean, here's the standard deviation, calculate a 99% confidence interval, calculate a 90% confidence interval. I will always specify. So when I ask for a 95% confidence interval, you have to find the corresponding z-value. So I know it's 1.96, but you know, because I've been doing this for a long time, but you know, I don't expect you all to have that kind of stuff memorized. However, let's go to our, so here's our standard normal z table, okay? So how did I get that 1.96? Well, if you flip over here, 1.96 is right here. Now you might be saying, the area beyond z is 0.0250. That's a proportion, so you know, make sure you know the difference between proportions and percentages, obviously. If you convert that to a percent, it's 2.5%. But you might be asking, well, we wanted a 95% confidence interval. What, 2.5%? Then there's still 97.5% left. But don't forget that this is just one side. Oops, sorry. This is just one side of the distribution. So let me draw it out for you just so you can see what I'm talking about. So if that's your standard normal curve, we've got our x bar is what, 7.5, right? That was the mean number of commuter hours traveled at the university, right? And in Z language, what is that? Well, it's 0. How different is the mean from the mean? It's not. So what we found was that at that, let's go up here first, at that Z equals 1.96. Can you see that? Yeah, Z equals 1.96. What it's telling you in the book is that the area beyond Z is 2.5%. Let's go back to it. Right here, 2.5%. And the area between the mean and the Z is 47.5. Well, it's 0.4750, which if we convert that into percentage 1, 2, that's 47.5%. But remember, that's only half the curve. So it also tells us that for negative 1.96, it's the same thing. You have 2.5% in this little bit here, and 47.5% in that bit. Well, if you add these two up, it's 95, and you add these two up, right? That's 5%. So what it's saying is that with a z of plus 1.96 and a z equals z of negative 1.96, that between that, you've got 95% of the data. Right? That's all that's all that is. If you find that complicated, I'll give you a nice little kind of quick and dirty way. Just you'll have to do a little memorization, but it's pretty easy. If you go back here, I'm only going to ever ask for 95 or 90. Well, I'll only ask for 95% confidence intervals or 99%. Sometimes I could ask about 90, but I think on the homework, maybe I'll just make it more simple and just ask for those two. So you know what the z-score is there. So if I ask for a 95% confidence interval, boom, there's your z-score. If I ask for a 99% confidence interval, boom, there's your z-score, okay? If I ask for a 68% confidence interval, that would be your z-score. Now, obviously, that's too low. Again, it's just sort of typical practice for scientists to like that 95. I've thought about this for a long time. There's nothing magical about it, but it's just sort of convention. It's just kind of the way people do it. So I'll ask about those, and I'll just keep it more basic for you. So if you're hung up on looking that up in the book, well, just memorize that when I ask for a 95% confidence interval, it's going to be z equals 1.96. If I ask for a 99% confidence interval, the z is going to be 2.58. Just to keep it simple. Okay. All right, so going back to the example, here's our standard error of the mean. We calculated it. Now to calculate the confidence interval, so we've got this value here. And once I ask for the 95% confidence interval, you know the z. So now you're able to fill in the z and the z-score corresponding to the confidence interval, the confidence level, 95%, and then you multiply it by the standard error. Okay, so here's the equation. It's really simple. The math behind this is not hard. I actually feel like this, for whatever reason, this lesson always seems to go pretty well in person. I'm not so concerned about estimation. I think you guys will get a good grip on this. More fun stuff to come later, though. So plugging it in, a 95% confidence interval. So where did that 7.5 come from? Well, that's our sample mean. I gave you that, right? From the sample, the mean number of hours commuted was 7.5, plus or minus z, which we got was 1.96, times the standard error, which we calculated at 0.07. So here's the calculation right here. And notice here that this is plus or minus, okay? So here's our point, and then we plug in our z multiplied by the standard error. Here's the calculation here, 1.96 times 0.07 is 0.14. So you have 7.5 plus or minus 0.14. And that's pretty much what I was talking about before. So we have that point, we have that point estimate, x bar equals 7.5. But we want to draw that confidence level around it, right? And what you got was 7.5 plus or minus 0.14. So in order to tell where the bounds are, you just add 0.14, which would be running out of lead. 7.64, right? 7.5 plus 0.14, and then 7.5 minus 0.14, which is 7.36. Which is exactly what I did here. So what does that actually mean? This is one of the, we're kind of moving into the times when I'm going to, with the inferential statistics, I sometimes like to call them Mad Libs, where it literally, your sentence will always take the same format. You just kind of fill in the blanks. So what you'll always say, so here's the conclusion from the example, but your sentence when we go back, go back here, the steps, so we did this. We calculated the standard error of the mean. First thing we did. Confidence level, got the z. That was the 1.96, we got that. We calculated the confidence interval. We got our between 7.36 and 7.64. The next thing, the most important, is interpreting the results. You will always write in this format. We are blank % confident that the true mean blank, whatever variable you're looking at, is between blank and blank, and then refer to the population. So let's talk about that in more real terms. So in this case, I asked for the 95% confidence level. So we are 95% confident that the true mean, what was it? It was the commuting time, is between 7.36 and 7.64 hours per week. Make sure you refer to your units on our campus. Refer back to the population. Remember, we took the sample of people from the population, but we're trying to make conclusions about the population. We don't really care about the sample as much. So you might be looking at this and saying, what happened to the sample mean? Well, we knew that sample mean was 7.5, but in order to know, in order to calculate like the actual range or how confident we are that what we calculated is representative of the population, that's why we had to do that confidence interval. So here's your confidence interval here, 7.36 and 7.64. Now sometimes it's reported as just the plus or minus whatever the confidence interval is. So another way to say this would be that we are 95% confident that the true mean commuting time at our campus is is 7.5 plus or minus 0.014 hours per week. That would be the same as, so think back to like the political example. Candidate A is polling at 40% plus or minus 3. You've seen that before. That's this, plus or minus. The real way to, when you see that data, what they're really saying is rather than 40 plus or minus 3, what they're saying is that they're confident that the actual percentage that candidate is polling at is between 37 and 43. You see how I just took 40 and subtracted 3 and then added 3? Because the confidence interval, so if it's let's get a little more room here. If it's 40 plus or minus 3, well, that means that the confidence interval is between 37 and 43. So when a pollster comes to you and says, well, this candidate is polling at 40%, it doesn't really mean anything because that's just a point estimate. You should ask them, what's the confidence interval? And then when they say it's plus or minus 3, the next question you should ask would be, what's the confidence level? Are you 95% sure? Are you 99? Are you 90? What z-value did you use? I guess if you really want to test those pollsters, see what they're doing. So this to me was a mistake that was made in the polling data in 2016. So many people made the claim that Hillary Clinton was polling above Donald Trump the whole time, though Donald Trump won, and people wanted to say that, oh, the statistics that were collected weren't accurate. No, the issue was that while Hillary Clinton was polling slightly above in most cases, if you looked at the confidence interval for Trump and Clinton crossed over. So it was sort of, I think it was just a general misinterpretation of how estimation works. So, hopefully you're a more a more literate consumer of this thing moving forward. Okay, so here's visually what's going on there, right? So here's your sample mean, your point estimate. We created that confidence interval in knowing, so where did the 1.96, where did that come from? Well, I asked for that. That tells me I'm 95% confident. Where did that 0.07 come from? That's the standard error. We calculated that using the standard deviation divided by the square root of n. That's that simple formula before. So what we're really saying is that we are 95% confident that the true number of hours people at the campus spend commuting is between 7.36 and 7.64 hours a week. So in generating this number, if the true population number is 7.37, then this is right. Or if the true population, commuting time is 7.64, this is right. Because point estimates are always bounded by a confidence interval, always. It's kind of like, think back to before when we calculated a sample mean, and I said you need the variation, right? You need the standard deviation. We calculate a measure of central tendency and variability. Same thing as here. We've got our central tendency. This is the sample mean. This is what grounds us. But there's always error. There's always variability. That's why we calculate that confidence interval. Okay. So one way to reduce the risk of being incorrect is to increase the confidence interval, obviously. I mean, think about it. If I said I'm 95% confident and you say, well, I'm 99% confident. Well, the chance for error is higher for me because I'm only 95. You're 90. You're 99. Somebody who's only 90% confident is less, and so on and so forth. So we could do a 99% confidence interval for commuting time. And I'm going to do that myself here. Did I do it? No, that's the other example. I wish I didn't work that one out. If we did a 90, let's work it out here. Flip over here. So we have our confidence interval is equal to 7.5, that's our x bar, plus or minus z times the standard error, right? So 7.5 plus or minus. So the z for a 95 confidence interval was 1.96. For a 99, it's 2.56 or 2.58. Hold on. 2.58. Sorry about that. There you go. Memorize those numbers. Okay, so plus or minus 2.58 times, our standard error doesn't change. It's still 0.07. Okay, so here's the formula for that. So I'm going to go and I'm going to just put this down for a second and pull up the calculator. Okay, so here we are, calculator. So we got 2.58 times 0.07, 0.18, and I'm fine if you round it just to that, okay? So this section right here is 0.18. So if I'm going confidence interval 99%, I've got 7.5 plus or minus 0.18. When I subtract 0.18 from 7.5, I get 7.32. When I add 0.18 to 7.5, I get 7.68. So the way to say this would be, we are 99% confident that the true mean commuting time for our campus is between 7.32 hours and 7.68 hours. How does that compare to what we had before? I'll take a look. Here we've got 7.36 to 7.64. These are minor differences, but do you see how 7.36, this is lower. So do you see how the confidence interval here got bigger? So it's kind of like as our confidence goes up, as our confidence level goes up, the confidence interval gets larger. As the confidence level goes down, our confidence interval also goes down. I mean, think about it. I could say I'm 2% confident that the true, that would be an even lower confidence interval. If I went to 99.99999% confident, well, then I'm going to have to use a z of 4, which would increase the confidence interval. And I think it makes sense. I mean, it maybe best to move away from the math a little bit and think about it. I mean, I could say that I'm, think about, let's see. I guess think about how, if you say you're more confident, then you have to include a larger range. I mean, so for instance, with the commuter hours, I could say I'm 100% confident that the commuter hours is between 0 and 100. But what good does that really do? I mean, we're really confident. In fact, I'm so confident that I'm positive. But if it's between 0 and 100, what does that really tell us? It doesn't, that's too wide of a range. So researchers are always kind of grappling with what point do I, sacrifice a little confidence for a little more precision? That's really what it is. So, the example for the 1.96, the 95% confidence level, well, it's a little more precise, but you sacrifice a little confidence. Here, your confidence interval gets bigger with the 99%. So you have more confidence, but you're sacrificing a little precision because you've increased your range. Okay? So see, I didn't need to work it out. Here it is right here. So this is a really good slide. This is slide 14 on the PowerPoints, but this illustrates what I'm talking about, where the precision and confidence are kind of balance each other out. So we're 99% sure that it's within this range, but there's still a 5% chance that it's outside. We're 99% sure that it's within this range, but there's a 1% chance that it's outside. See how this range is bigger than this because we're more confident in this than we are this. And it'll always work that way. The lower your confidence, the tighter your confidence interval. The higher your confidence, the wider your confidence interval. Okay. So I had this slide first, but I felt like it would confuse you, I didn't think it would confuse you. I think it just would distract from the main point. But the main point is that typically we don't know the standard error of the sampling distribution. Typically we don't know the standard deviation of the population. In fact, 99 out of 100 times you won't know that. So you might be saying, well, if you don't know the standard deviation, how can you calculate the standard error? Because the standard deviation divided by the square root of n is the standard error. Well, what we know is that, so here it is right here. Yeah. So if we don't know the mean and we don't know the standard deviation, because that's what we're trying to estimate. We're trying to make conclusions about the population. All we have is a sample. I'm not going to work it out mathematically. It's just too much to try and do over a video online. But if you think back to the central limit theorem, just trust me that if the sample size is greater than 50, if you have a large enough sample size, then the sample standard deviation is a good estimate of the population standard deviation. And I need to rid that because that's the standard error. So basically we can use the sample standard deviation to estimate the population standard deviation. So here we are, we're trying to estimate the standard error, but instead of using the population standard deviation, which we typically don't know, we use the sample standard deviation, and that gives us an estimate. And again, I could show you the math. It's just too complex for this. Just trust me that the logic of the central limit theorem is that if you have a large enough sample size, you can use that sample standard deviation to estimate the population standard deviation. Okay, so let's do a little example. So I've got the number of TV hours that Americans watch, which I bet in the last week or so has gone up. It has for me. Okay, so we take a sample of 1,000 people. How many people live in America? It's about 100. It's about 328 million. Okay, so here's our sample. Here's our sample mean. I'll give this to you, though you could calculate it. I won't ask you to calculate that on your own. And the sample standard deviation. So think this is stuff we've done. This is beginning of the semester stuff. Calculate the mean, calculate the standard deviation for the sample. Okay? So now, in order to calculate confidence interval, these are the three pieces you need. You always need your sample size, you always need your sample statistic, the mean, and you always need your sample standard deviation. If you have all these things, you can calculate the confidence interval. So remember, the first step is to calculate the standard error. Here's the equation. The standard error for the sample, which is an estimate of the standard error of the population. Again, we can use that as a fill-in to estimate that. It's the same equation as before. It's just that rather than the population standard error, we are calculating the sample standard error and using the sample standard deviation instead of the population because they're good estimates. If we have a large enough sample size, then it's randomly selected. That's a mouthful. Okay, so we take that sample standard deviation, divide it by the square root of the population size, and we get our sample standard error. I asked for a 95% confidence level. Where did that 2.94 come from? Well, I gave you that. That's the sample mean. So the sample mean plus or minus, where'd the 1.96 come from? That's the z-score that corresponds to a 95% confidence level. Had I asked for 99, you would have 2.58 here, right? And then you multiply it by the standard error, which is what we calculated here. 1.96 times 0.08, you get 0.16. So the margin of error is 0.16. So we have the mean hours of TV viewing in the United States is 2.94 plus or minus 0.16. When we subtract this from 2.94, we get 2.78. When we add 0.16 to 2.94, you get 3.1. So we can say that here's the Mad Lib again, we're 95% confident that the true mean hours spent watching television per day by people in the United States is, you could say not less than 2.78 and not more than 3.10. It's just another way of saying we're 95% confident that the true mean is between those numbers, right? So just another way of saying it. But what we did was we got this, here's your confidence interval, and we're 95% sure that the true mean falls somewhere in between this value. So going back, our estimate of 2.94 is correct if it's between these two numbers. Even if it's 2.78, even if it's 3.10, this point estimate is still representative of the population, the true population mean, because it falls within the bounds. Okay? So one kind of last thing that I'm going to throw at you, think about this. So in this example, we got a sample of 1,001, and our sample mean and our sample standard deviation. The calculation of the standard error is here. It's pretty straightforward. What would happen if your sample size gets really big? Imagine that we took a sample of 10,000. Well, taking the square root of 10,000, you're going to get a larger denominator, which is going to push this number down. Let's say you only took a sample of 2. Well, then you're going to get a smaller denominator, which this number will go up. So you could be thinking that the larger the sample size, the tighter you get your confidence interval. So there's kind of two ways to increase your precision. Because we want to be as precise as possible, but there's two ways to sort of narrow that confidence interval. One way, increase the sample size. Another way, lower your confidence, right? So if your confidence level goes down, the bounds get tighter, right? That was this right here. As your confidence level goes down, the size of the confidence interval goes down. If your confidence goes up, if you want to increase, be more confident, then that's going to drive your confidence interval up. The other way to adjust it is adjust your sample size. And this is what social scientists do. This is why we need large enough sample sizes, because if the sample size is too small, first of all, if the sample size is under 50 or so, then we really can't do much with it anyway. But one reason why people always want to get their sample size up is because with a larger sample size, you're going to be more precise with your confidence interval. You're going to be able to narrow in on that population number more precisely than you are with a smaller sample size. Okay, so let that kind of digest a little bit. What I'm going to show you on Tuesday, I'm not going to introduce anything new. It's just going to be like build on this a little bit. But I would say of the two, this is estimation part 1. Estimation part 2 is going to be, there's not going to be as much new stuff. Let's just put it that way. And then for your homework, you're just going to be calculating some confidence intervals. So like I said, I'll put up a little cheat sheet of the formulas just so you're not having to dig around. But the only formulas you need here are this one, right? So this is the true formula, but we can use the standard error of the sample and then the standard deviation of the sample to estimate this, because we typically don't know it. And then the key one is the confidence interval equation right here. So those are the only two equations that you don't need to memorize it, obviously, but you'll be using for your homework. And this slide's important too, slide 8, because these are the steps. This is the first thing you do. I give you the stuff, calculate the standard error of the mean. Decide on the level of confidence. That'll typically be me giving it to you. And then, so if I say 95% I want you to calculate a 95% confidence interval, you got to find the z-value. Why? Because you need it for the equation. Okay. And then you get the z-value. Then you calculate. Then do the math. And then interpret the results. Use the MATLAB. You always got to tell me how confident you are, what the value is, and the the confidence level, the confidence interval. You got to tell me what the range is. You got to tell me the units. Are you referring to hours, money, years, whatever? And then you got to make a reference to the population, who we're talking about. American TV hours, students at VSU and their commuting time, fiction books by Mark Twain, whatever. But always refer to the population that you're looking at. Okay? So that's all I got. I am right in under 50 minutes, so sorry. I feel, when I'm doing this, I always feel like I can make the videos shorter than I do, but hopefully it's not... Hopefully this isn't boring you. Hopefully it's helpful. One thing I will say is if you have any suggestions on how I can do this better, please tell me. I am by no means a professional at this. I've never done this in my life. It is very, very new and, frankly, kind of nerve-wracking for me. So if you have any suggestions on something I could do better or make it clearer or helpful, email me, let me know. But the homework's going to be really straightforward, and obviously I know with the situation that it's harder for you guys to do this. Trust me, I respect you for being able to even do the stat stuff online. It's impressive. I'm looking for effort. So what I don't want to see is people not trying or not turning stuff in. That's going to be a little bit problematic. But if you're turning stuff in, I'm gonna take care of you. So just please do your best. I know that the situation is far from ideal. Let's do the best you can. ask me questions. I'm here. I'm here to field questions. We can go over stuff. I'll give you examples. I have a feeling when I post the homework, I'm going to get more questions, and that's totally okay. So good luck, and stay healthy, stay safe. I'll talk to you, I guess. I'll upload the next video. Will be coming on Tuesday. So have a good weekend.